everyone, and thank you for the invitation and the opportunity to present. And, so I will talk about the stochastic sandpile model. So first, let me define the model. So it was a model which was suggested by Mana, a physicist, in the 90s. In 91, and it emerged as a variant of the abelian sandpile model, as Lionel Levin explained. And so sometimes physicists refer to it as the Mana model, but it's the same model. And so the idea came from the fact that physicists figured out that the abelian sandpile model did not exhibit the universal behavior that we hoped it would exhibit. And so they introduced a modification of this model, introducing more randomness in the model so that the model has better mixing behavior and has a behavior which becomes more robust and less sensible with respect to the initial conditions or to the lattice, for example. And it can be seen also as a cousin of activated random walk. It is it resembles So it looks a bit like activated random walk, which was in turn introduced as a variant of the stochastic sandpile model, which was more tractable mathematically. And then the mathematicians concentrated on this other model, but then maybe most of the techniques developed for activated random walk can also be used for the stochastic sandpile model. So this is what we did in this work. So let me go with the definition. So we have grains which move on the graph, and we'll define, for example, on ZD. So grains of sand, if you want. And so configuration of the model is just a vector indicating how many grains are there on each side. So it's a vector eta from ZD to n. And so eta of x is the number of sand grains at position x. And then we start with an initial configuration, which is random. And for example, we can start with eta 0 of x on each side of ZD, which are IID with a Poisson distribution of mean mu. So in fact, the precise law does not matter much, but the important parameter is the mean number of grains on each side. And then the dynamics is defined as follows. We say that a site is unstable x is unstable at time t if simply it contains at least two grains. Yes, sorry. So if a site contains at least 2 grains, it's unstable. And when a site is unstable, then at rate 1, it topples And what does it mean? It means that it sends two of its grains on neighboring sites chosen uniformly. Chosen uniformly and independently. And so it's a continuous time model, and so we have like an exponential clock at each site, and when this clock rings, if the site contains at least two particles, then you take two particles and you make them make one random walk step, and independently, so it can happen that they jump on the same neighbor. Okay, and then we let the configuration evolve, and the natural question is, does the model eventually reach stable configuration, so with on each site only 1 or 0 particle? And so obviously on ZD it never happens because there's always somewhere at least one site with at least 2 particles. But we have the following notion of fixation. And okay, so let me. So which enables to talk about the phase transition. So we say that the system fixate if 0 is visited only finitely often, only a finite number of times. So we have the dynamics on ZD, and we say that the system fixates if we have only a finite number of visits of the origin, and it turns out to be equivalent to saying that each finite subset of ZD eventually becomes stable and does not move anymore. And it's also equivalent to having each particle only walks a finite number of steps and then remains somewhere forever. And we have the following phase transition. So there's a result by Rolla and Sidoravicius. In 2012, which says that there exists a critical density mu c such that if mu is strictly less than mu c, then the system almost surely fixates. And if mu is strictly larger than mu c, then the system fixates with probability 0. And so we have a phase transition, but to say that we have a real phase transition, which is really interesting, we have to check that this mu c is strictly positive and that it's strictly below 1. So it's the first natural question. Is mu c strictly between 0 and 1?
What is the graph on which you take this?
On a ZD.
ZD. So and no matter what dimension.
Yes, for each dimension there exists a mu critical, which will depend on the dimension. And so there was the first result by Rolla and Sidoravicius in the same paper. Showing that, so first thing we can say is that mu c is at most 1, because it's clear that if you have on average more than 1 particle per site, you will not manage to fixate. Because in the final stable configuration, you have only at most 1 particle per site. And they also obtained that mu c is at least 1/4 in dimension 1. Then there was a result of Sidoravicius and Teixeira. In 17, showing that mu c is strictly positive in any dimension. So they show that for sufficiently low density, the system managed to fixate. And then this lower bound 1/4 was improved to 1/2 by Podder and Rolla in 21. And then finally, Hoffman, Hu, Richet, and Rizzolo showed in 2022 that mu c is strictly less than 1 in one dimension by adapting a technique that was developed to show the same thing for activated random walk. And so the result I want to talk today is that mu c is also strictly less than 1 in all dimensions. And so until now, most of the efforts on the model was concentrated on this question to show whether mu c is strictly between 0 and 1, because well, we need already this as a first step before we study more in detail the phase transition. So let me see. Yes, and our technique also adapts a technique developed to study activated random walk and to obtain the same result for activated random walk, but with some technical challenges to address to adapt it to the stochastic Sandpile model. So the first idea to show this is that it's enough to study the phase transition of the model on ZD. We can study the model on the torus. So we take a box of size n and with a periodic boundary condition. And so now we have a model on a finite graph. And on this finite graph, the questions are a bit different because at least if you have not more particles than the number of sites, you're sure that sooner or later it will fixate. So the relevant question is not anymore does the system fixate, is how long does it take to fixate? So in this setting, the interesting thing is the fixation time. So if you want, it's the first time t, such that for all x in Tn, eta t of x is at most 1 for the continuous time model on the torus. And what we expect that we have the following phase transition, that Tn should be over the log n if mu is below mu c, and Tn should be exponentially large in the number of sites of the torus if mu is supercritical. So if you want, it's another possible definition of mu critical, and so it's one of the many universality conjectures that this phase transition should coincide with the phase transition of the fixation on ZD. And so to obtain that there is an active phase, so a phase in which the model does not fixate on ZD, what we show is that we have a phase in which Tn is exponentially large on the torus. So we showed theorem 2, if you want, if this is theorem 1. So theorem 1, for mu strictly less than 1, sufficiently close to 1, there exists a positive constant c, such that for all n, Tn is at least exponential Cn to the d with probability tending to 1 when n tends to infinity. And in fact, we even have with probability 1 minus exponentially small. So we want to show that with overwhelming probability, the stabilization on the torus takes exponentially long time. So the idea, if you want, is that the torus, if you are supercritical, it's in a kind of metastable state. It's there is only it will reach at some time the stable configuration with only sites which contain at least at most one particle. But it will take a very long time to reach this stable state.
So is this dichotomy also established for the torus?
No, it's not established. Maybe I guess that I'm not sure, but I guess that we can show that for very small mu and mu very close to 1, we have this behavior. Well, we can show that for mu close to 1, we have this behavior. And for mu close to 0, I guess maybe the results imply that we have a fast stabilization, but we don't know this dichotomy precisely. And then, let's show, so I will try to explain how we show theorem 2. And then we have that theorem 2 implies theorem 1 is more easy because if you know that the torus takes an exponentially long time to stabilize, then you can show that when you stabilize the box with open boundary conditions, then a fraction of the particles exit the box. And this is known to be a sufficient condition for the system to be in the active phase on ZD. Because if a fraction exceeds each box, then you take a box, a fraction exceeds, and you restabilize the box neighboring, a fraction exceeds, and you never manage to stabilize. This is the idea, roughly speaking. So let's concentrate on this. And so since we are on a finite graph, we can consider a discrete time version of the model. And so we only have to show that it takes an exponentially large number of topplings. It's enough to show that this time is large. So we want to show that it takes exponentially many topplings to stabilize. Okay, so now let me introduce the magical tool that Lionel Levin already mentioned, which is the abelian property. And the other very important trick, which is half topplings. So the idea for the abelian property is that we consider a stack of instructions. So we consider an array, if you want, tau. So for each site of ZD, and you draw an infinite sequence of instructions, which are independent variables. And each tau xj is a jump instruction to a neighbor of X chosen uniformly. So if you want, you have your torus. Let's say we're in one dimension. And above each side, you draw an infinite sequence of arrows which point to one of the two neighbors. And then the idea is that we can make the model evolve as follows. When we have to topple a site, we use two of the instructions in the array, and then we mark them as used, and we go on like this. And so we have to recall the number of instructions that we used at each site during the process. And then the abelian property simply tells you that the order with which you do the topplings is irrelevant. So let me maybe write it here. For any fixed realization of tau, the order of the topplings is irrelevant. And so it holds for any fixed realization of tau, so it's really a deterministic property. And so what it means is that you can choose any order to topple the sites as long as you only topple unstable sites. As long as you follow the rules, you can use any order, and the resulting configuration and the number of topplings does not depend on the order. And then we want to use this in a clever way because there's something annoying in this model that we always have to move two particles at the same time. And this is the point that makes things difficult. And to gain some independence, we want to allow also to move only one particle. So this is the idea of half topplings. So we want to allow to move only one particle. So the idea is simple, is that when you have the dynamics, you can maybe use only one arrow. You move one particle on the neighboring site, and then you recall, okay, here I use only one instruction. I should have used two, so maybe later on I will use the second one. So let me do an example. So let's say that we have this configuration with two particles on a site X and one particle on the neighboring site. So this is eta 0. And let's say that we have the following arrows. So let's see how the model evolves doing half topplings. So we can start with this site. We can see that it has two particles, so it's unstable. So I should use an instruction. Okay, I use this one. And I move one particle on the neighboring site. So I obtain this configuration. Now this neighboring site becomes unstable. I should use some instruction. It moves one particle on the neighboring site. And I obtain this configuration. And now, is it over? Because each site contains at most one particle. No, it's not over because at these two sites, I used only one instruction. And I should have used one more. So to complete the process, I should use one more instruction here, moving this particle. I obtain this. And then we have an unstable site here because we have two particles. So I should use one instruction here. It moves there. And I obtain this configuration. And now it's really stable because at each site I have at most one particle and the number of instructions used is even. And this, we call this a stable configuration. So this is simply the ID. So during the process, we keep track of eta h, where eta is the configuration of particles. And h is the number of instructions used at each site. That we usually call the odometer. And we have this new definition of a stable site. A site X is unstable for a couple eta h if eta of x is at least 2, it's unstable, or if eta of x is 1 and h of x is odd. Because this means that I have used one instruction, I should have used one more, so this particle is not really stable, it should have moved. And once I have on each site eta of x equals 0 or eta of x equals 1 and h of x even, then it's stable and it's as if I had done proper top links moving two particles at a time. And so doing like this, so we are allowed to use one instruction at x if it is unstable. And then we have the same abelian property for half toppings. So we can choose we can do the half toppings in any order. And so we call this a half toppling when we use only one instruction at a site. So now we have this initial configuration and we look for the number of half topplings that we have to do before we reach a stable configuration. Okay, so now we study the number of half topplings.
Can we switch the... Can you switch the...
Yes, okay. Or maybe it's okay if I do this. And so we call this a half topping. And so now, so it's a bit simplified because the particles, we can move them one at a time, but then the crucial point is to control at each time the parity of the number of instructions you used at each site. And this is always the difficult point. Okay.
Is this number two moves at a time, is it important or?
No, it could be any k. You could replace this 2 by k. But in the original model by Mana, it was 2 because it's the simplest case, and I don't think it changes a lot because well, his article was called a two-state model of self-organized criticality, because then the stable configurations are configurations with only zeros and 1. So it's the simplest thing you can think of. Well, if you roll out, if sites are unstable as soon as they contain one particle, then it's never stable. No? Sorry? Ah, you move one particle when you have at least two, but then the particle below will never move, I guess. So, I think. The idea is really to model, to have a phenomenon of self-organized criticality. So we need that the system is able to accumulate some tension if you have too many grains, too crowded, and that adding some grain can be able to release all the tension by triggering a large avalanche if you had too many grains. So, so now let me tell what is the general strategy. So we start with the number of particles. Remember, it was a Poisson with mean mu times the number of sites. And so to simplify, I can assume that it's equal to mu n to the d. It's not a great deal. So we start with this number of particles, and then we're interested in the probability that the system fixates in less than exponential Cn to the d steps. And a first idea is that if the system fixates, then the final configuration is one particle on each side of a certain subset of the torus. So we can write this as a sum on all subsets of the torus with cardinality exactly mu n to the d of the probability of the same event and with the final configuration, let me write it eta final, is the indicator of the set A. So the particle eventually stabilizes on A. And we want to show that this is exponentially small, and so here we will have a combinatorial factor, but if mu is close enough to 1, we can afford this because it will be an exponential with a very small constant in the exponential, so it will be beaten by this. So we can afford this, and now we concentrate on a fixed A and try to show that this is exponentially small. And then so you have this sum on A, and for one fixed A, what you can show is that the above probability is less than the probability of the same event if you add the constraint that half couplings are allowed out of A even when the odometer is not odd. So we modify the models by saying that if a particle is alone on a site out of A, we are able to topple even if it's not odd. Allowed on A complement with on site with at least one particle, regardless of the parity of the odometer. Because if the above event was realized, then in this setting it's also realized, because if you had this, then you had a way to half topple the sites so that you reach so that this happens, and so allowing more things does only increase the probability. And now we have this simplified model because with this new rule, the particles can only stabilize on the set A, because on the set out of A, they're never stable. So I could also remove this, in fact, because with this modified rule, we are sure that the final configuration will be on A. But the question is, how long does it take to stabilize on A? And so once we have this, we reason with the fixed A. So, and let's see what we do for a toppling strategy. So let's call A the dormitory. So it's where the particles are supposed to go to sleep.
So on the side of A, you just have random walks.
Yes, out of A, the particles walk and never stabilize until they reach a site of A. So we can do the following thing. First step, half topple the sites of A complements. Until all the particles are on A. And so this we are allowed because out of A we can always do half toppings regardless of the parity. And then second step, we want to have one particle on each side of A. So if we have sites of A with at least two particles, we make one of them move until it finds an empty site of A. As long as there exists x in A with a eta of x at least 2, we move this particle until it finds an empty site of A. And so we can do this because when we have at least two particles, we are always allowed to do a half toppling. And so after these two steps, we obtain the configuration eta equal indicator of A. All the particles are on A, and we have a certain odometer that we don't know. The odometer may be odd at some sites and even at some other sites. So some sites of A are stable, and some are not.
But in the second step, your particles move out of A and come back.
Yes, they also move out of A, but out of A we can move
Out
them.
of A,
Yes.
random walks and come back.
Yes. And then third step. So now we have these particles on A and we have to stabilize them. And for some technical reason, we fix B included in A with no neighboring sites in B. You will understand just later that why we fix this B. So for example, think of a chessboard and you keep only the black sides of A. Or the white, as you prefer. So you fix this set B, and then as long as there exists X in B such that the odometer at X is odd, so we try to stabilize first this set B. So as long as we have an unstable site in B, we try to stabilize it. And how do we stabilize it? So we topple this site, and then we make this particle move until it comes back to its starting point. as long as there's an unstable site, we choose such a site. In a clever way, I will talk about this later. And move one particle from X until it comes back to X. So you can move it until it comes back to X, because out of A it is allowed to be toppled, and the other sides of A, they're already occupied. So when it goes on another side of A, you have at least two particles, so you can go on. So you make a loop from X going back to X, and after this loop, so before this loop the odometer was odd at X, and after the loop it becomes even, because you did one toppling at X. So after this loop, the odometer, the number of half topplings you did on X, it becomes even. So the site X becomes stable, but the interesting point is that along the loop, the particle may have visited many sites of A, and it can have made stable site become unstable. But the tricky point is that it can also have visited unstable sites, and have made them become stable. So along the loop, the parity of the odometer at other sites so at the sites that we visited, so the parity changes depending on the parity of the number of visits of this loop to other sites. And so the key point will be to show that it wakes up more sites than it makes sites become stable.
What if H is even for all?
If H is even for all B, it's the end of step 3. And then we have step 4, and we just conclude the stabilization. So at some point, all the sites of B have an even odometer. And step 4 is just to conclude the stabilization. And so the really interesting step is step 3. And the idea is that we will lower bound the fixation time by the number of loops during step 3. And so the crucial point is to control the parity of the odometer both at two moments. So at the beginning of step 3, because you remember that after the second step we have to obtain one particle on each side of A, but we don't know what's the parity. So we need a control on the parity of the odometer at the beginning of step 3. And also during step 3, we want to know how does the parity of the odometer evolve at different sites. And we do this using the following key lemma. Whose idea is simply to show that if you visited some point a certain number of times, then with positive probability you visited it an odd number of times. This is simply the idea. But there's some technical issues hiding behind it. So during steps 1, 2, and 3, for every x in B, conditioned on the fact that eta t of x is equal to 1. Well, during step 3 it's always the case, so it's not very interesting to say that. And knowing that since the last time that you moved the particle at x, it was visited by at least some other particle. So knowing that x was visited by some other particles, since its last move. So since the beginning, if x has never moved, or since the last time that you chose the particle x to make a loop. So knowing this, the odometer at x, so the odometer which is ht of x, is odd with probability at least a constant which only depends on d. And so this is the key issue, because if we have this, then we can show that, then we can obtain that after the second step, the parity of the odometer at the sites of B dominates IID configuration, because each site is odd with a certain fixed probability. Yes, I forgot to say. The important point also is that this holds independently for different sites of B. And you also have that during the third step, each time that you want to choose a site that was visited, you know that the odometer is odd, at least with this probability. And it's key that we only choose we only consider sites of B with, remember, the set B has no neighboring sites. And this is to have this is needed to have this independence. Because, well, it will be clear if I explain a bit the sketch of proof of this lemma. So, sketch of proof.
And B must be a fraction of A or rho.
Yes, if you have A was a proportion mu close to 1 of the sides of the torus, and you remove half. So B remains a proportion of the sides of the torus. This is the important point. So let X in B, and assume, so we condition on the fact that eta t of x equal 1 at a certain time t of the process, and x was visited during since its last move. And also assume that the odometer is even, and we will show that we can modify a bit what happened to make the odometer become odd. So the ID, recall that we had this stack of instructions above each site with many arrows. So we modify this stack of instruction tau. We modify the array tau to make the odometer become odd. And the idea is simple, is that we consider the last moment when x was visited before t. And then we can find a neighbor of x which either is not in A or was occupied at that moment. So this sounds a bit like a technical detail, but it's important. And we can see that such a neighbor exists, because if it did not exist, then all the neighbors of x would be in A, and they would all be empty at the moment of the last visit of x. So you would have this site x, the neighbors which are empty, and someone came to visit x. But remember that if someone comes and this belongs to A, this belongs to A, on the sites of A, if you arrive, you stop. So it's impossible that someone from the outside visited X. So the visit at X must have been by some particle coming from X. And then you can figure out that the only case is that X started with two particles, and one of them at this moment jumps on one neighbor and gets trapped here. And you can see that in this case, the odometer at X is 1. So it's odd, and it's what we wanted. So in fact, this case does not happen, and Y always exists. So it's a big technical detail, but it's the technical detail for which we need that we use this thing in a particular toppling strategy where we first move the particles on the sides of A and first make one particle come on each side of A and then topple B, first the sides of B. We need all this to make this lemma work. Okay, so then we can find this neighbor, and then the idea is simply that we add two arrows between X and Y. Precisely at this moment in the odometer. So the idea is that it will add a return trip from X to Y or from Y to X of the particle which came to visit X. So we had at this moment a particle which came to visit X, and with these two arrows it will make one more jump to Y and one more jump back to X, and this will increase by 1 the odometer at X. And we need that Y was not in A or already occupied to be sure that these arrows are effectively used. Because if Y was in A, for example, the particle which came to visit X, it will go to Y and then stop at Y. And it would change then all the future, and it will make a mess. So we really need this. And an interesting point is that, so it modifies the odometer at X, and you may wonder, yes, but doesn't it modify what happens next? No, because we consider the last visit of X before T, so then the rest of the story is not affected. And also, since y is not in B, because B has no neighboring sites, the change of the odometer, of the parity of the odometer at y has no consequence, because we never consider the sites out of B. And so, with this modification of adding 2 arrows, and we can show that it's an induction on all the possible stacks of instruction, and it shows that with possible positive probability, the parity was odd. And so, with this lemma, what we obtain is that, in a sense, we can couple the model with a small variant of activated random walk, because now we have that at the beginning of each loop, when we look at whether the parity is odd or even, we know that it's odd with a certain probability. So we can compare the model to the model where at each step, when you choose a site X, if it was visited, the parity, it's active with a certain probability. So this lemma enables us to couple the model with the variant of activated random walk. And so the idea is that we consider that a site is unstable if it has been visited since its last move. And saying things like that, you obtain that during a loop, a particle can only wake up other particles because it visits them. Then they become, oh, sorry, I want to say active. So you say that this site become active, they have been visited, and then knowing that the site is active, the odometer is odd with a certain positive probability. So it has a probability to be, in fact, not unstable or to be stable. And then, so then we can gain, this allows us to gain some independence, because then when you choose a site, the probability that it's that you can start the loop or not is independent of the past with this new model where you have a fixed probability of being active or not. And then you can implement the technique that was developed for activated random walk to show that for every fixed set B, it takes an exponential number of loops to stabilize. And this is done with a nice multi-scale argument. Of our joint work with Amin Asla and Alexandre Godillet. 23 or 24, I don't know, to show that we make an exponentially large number of loops. Exponentially large. Number of loops. I can try to explain in 20 seconds. So we have this set B, which is a certain subset of the torus, and we look at its connected component. Well, connected, it's a way to say, because the components which are not too much disconnected, let's say. And we show that for every connected component of a certain size, at least, it takes an exponentially large time in the size of this component to stabilize. And then we group the connected components in pairs, which are not too far apart, and we show that if it takes a large time to stabilize this and a large time to stabilize this, then the stabilization time of the union is exponentially large in the size of the union. And this is because when you stabilize this, it makes many loops, and some of these loops may wake up the other cluster, and then when you stabilize the other one, the loops will go to wake up the preceding one, and you will make a ping pong, having to stabilize this one, this one, this one, this one, and many, many, many times, which will end up in the stabilization time of the union being the product and not the sum, the product of the two stabilization times. And with this, you can go on in the different scales and showing that each time you have the stabilization time which remains exponentially large, and you lose a bit in the constant at each scale, but you end up showing that for the whole set, you have an exponentially large stabilization time. I think I will stop here, and thank you for your attention.
Questions?
Yeah.
So what do you use the geometric features of your graph, and which features do you need actually? You mentioned you use this also on transitive graphs, so not just the domains.
Yes, but this in the article was just for the other part, which was the lower bound on the mu critical.
Okay.
But here, the only thing we use, in fact, is the probability that starting from a site, a loop visits another site. So it's, if you want, something about the effective conductance between two sites. So it's quite robust in the graph. You only need an estimate on the probability that starting from X, you visit Y before coming back to X. Yes?
So I didn't totally follow the proof of the parity lemma, but is it obvious that introducing these cycles into this stacks of instructions doesn't create dependence between the parities at different sites?
Well, the idea is that we know that, so we assume that we have we condition on this event that X was visited since the last move and the resulting odometer was even. And we show that adding these two arrows does not change anything in the whole story of the process, except that at that moment, the particle makes one more jump and one more jump the other way around. And so it modifies the parity at X, but this has no effect at least up to time t, because it was the last visit of X up to time t. And it changes the parity at Y, but this has no effect because Y is not in B, and the parity of the sites out of B, we don't care about it, at least until step 3. That's why we don't consider step 4 when we topple the sites not in B, and we limit ourselves to step B, to step 3. So it's only, it's not, we didn't really couple the two models entirely, so it's only partly coupled in this particular situation. But still, it helps us a lot to reduce the difficulty to be able to have this comparison.
So the coupling works only if mu is very close to 1, and then you can decide in advance where you slip.
Yes, it works. Maybe it can work more generally because it controls. Well, it's all the works on the stochastic sandpile. It's always a matter of controlling the parity and having bounds on the probability that the parity is odd or even. So it depends on the setting you consider, but it's always this problem.
Yes. Sorry, you mentioned that you don't expect this to be very different if you set stable capacity to be 3 or 4. Do you think it would change much? Because here you have the very nice property that the size of A is exactly the capacity of. Like
Yes.
you know that if you match exactly the same quantity of particles, they have to slip there. Otherwise you would have to perhaps control particles
Yes,
living
right.
on a subset of this graph. Do you think this could
Yes,
be
I haven't. Must admit, I haven't thought about this in detail, so I don't know if it actually works. If this proof actually works for this larger model. But I don't know. You would have to see if this combinatorial factor does not become too large. I don't know.
Okay, so if no more questions, let's thank again Nicolas.